Hello and welcome to this video on set partitions and Stirling numbers of the second kind. We will define a set partition, give a few examples, and then develop some recursive formulas that we can use to count the number of ways to create set partitions. We obtain a set partition of the set of n things by splitting that set into a collection of subsets, which we call blocks. More precisely, a set partition into k parts consists of k non-empty and disjoint subsets, such that each element of the set n appears in exactly one of these blocks. So when we take the union of these blocks, we obtain the entire set. This slide shows an example of a partition of the set of 9 things into 4 blocks. We have a block containing 2 and 3, another block containing 4, 7, and 9, a third block containing 1, 6, and 8, and our final block is a singleton block containing the element 5. Just as a set is an unordered collection of elements, a set partition is an unordered collection of blocks. So I can list these 4 blocks in any way that I like. It's still the same set partition. Here's a nice visualization from Wikipedia of all 52 set partitions of the set 1, 2, 3, 4, 5. Singleton blocks, meaning those with one element, are isolated dots. Larger blocks are shaded in different colors. So here is the unique set partition into 1 block. And then we have the 15 ways to partition the set of 5 things into 2 blocks, followed by the 25 ways to partition the set into 3 blocks, the 10 ways to partition into 4 blocks, and then the unique way to partition the set into 5 blocks. We can now define the Stirling numbers of the second kind. S and k is the number of ways to partition the set of n things into exactly k blocks. So just as in the previous slide, we classified the set partitions according to the number of blocks in the partition. Let's calculate the Stirling numbers for the set of size 3. There are a total of 5 set partitions for the set 1, 2, 3. There's 1 set partition with 3 blocks, 3 set partitions with 2 blocks, and 1 set partition with 3 blocks. And here's something that's both interesting and useful. The Stirling numbers for 3, 0 and 3, 4 are defined to be 0 rather than being undefined. This is actually very important, as it will make our lives much easier when we define our recurrence relations for the Stirling numbers. And actually, this choice is really sensible. How many ways are there to partition the set 1, 2, 3 into 0 blocks? Well, that's an impossible task, because I need at least 1 part. In combinatorics, when someone asks, how many ways are there to do something impossible? The answer is 0. There's 0 ways to do something impossible. Likewise, there are 0 ways to partition the set 1, 2, 3 into 4 non-empty blocks. This is an impossible task because if I need 4 blocks, then one of them must be empty. Finally, you are probably wondering about Stirling numbers of the first kind. They actually have to do with cycle structure of permutations, and we will talk about those numbers later in the course. Next, I will show you the values of S and k for small values of n, and I will arrange these numbers in a triangular array, which should remind you of the structure of Pascal's triangle for binomial coefficients. This is for good reason. Our next task will be to show how to build the next row of this Stirling triangle from the previous row. Before I show you the values, we should note that the first row of this triangle corresponds to n equals 0. S00 is the number of ways to partition the set of size 0 into 0 non-empty sets. In other words, I want to create an empty partition of the empty set. Is that an impossible task? Like trying to partition the set of size 3 into 0 parts? Actually, this is not impossible. We trivially satisfy the requirements of a set partition by splitting the empty set into 0 parts. Let me explain why. If we go back to the definition of a set partition, we will see that every element of the original set must be in a unique block. And since the empty set has no elements, this condition is satisfied vacuously. So S00 equals 1, not just because it's convenient, but because it makes logical sense. We will encounter such trivial cases again in this course, and here is a productive way to distinguish these strange cases. Just remember, there are 0 ways to do something impossible, and there is 1 way to do nothing. In the case of S0, I do not have to do anything to create a set partition of the empty set. There are no elements to place into blocks, therefore there is one way to do this trivial task. So here are the values of the Stirling number S and K for set sizes between 0 and 5. We have S00 equals 1 at the top of the triangle, and then the left diagonal is all 0 because it is impossible to partition a non-empty set into 0 blocks. Now we could add some all 0 diagonals on the right where we try to partition into too many blocks, but we will leave off those zeros because we won't need them when we develop our recurrence relation. Now here's the bad news. There is no simple formula for S and K, the number of ways to partition the set of size n, into k parts. Mathematicians use the term closed formula to mean a simple expression. For us, this will mean that our formula should use our counting expressions, like n factorial and n choose k, but it shouldn't have a summation or a product sign or some other complex structure. Now here's the good news. There is an inclusion-exclusion formula, and we will derive that in a future video. But that formula will have a summation sign, so it is not a closed formula. Today we will do something else. We will give a recurrence relation for the Stirling numbers that will allow us to calculate any value of S and K that we desire. That sounds pretty useful to me. It serves the same purpose as a closed formula, even if it takes a little more work to get the number that we want. I want to say one more thing here because we have just encountered another of the recurring themes of this course. There isn't a closed formula for S and K because we've actually just asked a pretty hard question. The complexity of our answer reflects the difficulty of the question. And so if we start asking hard questions, we need to be prepared to revisit our idea of what a solution to that question looks like. All right, so let's get back to the mathematics. Here's the recurrence formula for the Stirling numbers of the second kind. Our first observation is that we can figure out the value of S and K by combining Stirling numbers for a set of size n-1. In other words, we can use the previous row of the Stirling triangle to find all the values in the next row. Let's see this in practice. Here's the top of the Stirling triangle that we saw before. Let's check that the Stirling recurrence is correct for 2 of the values in the row for n equals 5. Using the recurrence, S52 should equal S41 plus 2 times S42. And that's equal to 1 plus 2 times 7, or 15. Now how about S53? According to the recurrence, this is S of 42 plus 3 times S of 43, and that is 7 plus 3 times 6, which is 25. All right, so let's use the Stirling recurrence to find the row for n equals 6. The recurrence only holds for k between 1 and n, but we know that S60 is equal to 0 because it is impossible to partition this set into 0 blocks. And we can use the recurrence to find S61. It should be S of 50 plus 1 times S of 51, and that's just 0 plus 1, which is equal to 1. And of course, that makes sense. There is exactly one way to partition the set into exactly one block. Let's do one more together. The Stirling number for 62 equals S51 plus 2 times S52, and that's just 1 plus 2 times 15, and that gives us 31. Now I want you to pause the video and fill in the other 4 values of this row. I'm really serious. It will be helpful for you when we start to dig into the details of why this recurrence works. So here is the completed row for n equals 6 in this Stirling triangle. I hope these values match the ones that you calculated on your own. And if you didn't calculate these values on your own, and yes, I do mean you, then now is your second chance to pause the video and practice calculating 1 or 2 of these values using the recurrence relation. Check that the values you see here are the proper ones. So really pause the video this time and try it out. Now that we've checked this recurrence relation against some of the entries in the Stirling triangle, let's prove why it is correct. We are going to give a combinatorial proof that the left-hand side and the right-hand side correspond to 2 different recipes to construct a set partition. If you have trouble following this argument, then you should revisit the video and the exercises about combinatorial proofs. So let's get started. The left-hand side is straightforward. The number S, N, K is precisely the number of ways to partition the set of n things into k non-empty blocks. So the recipe for this left-hand side is literally pick a partition of the set of n things that has k blocks. So now let's consider the right-hand side. We are going to treat element n as special and pay attention to the block that contains element n. There are two terms on the right-hand side that we must add together, and we have learned that addition in a counting formula corresponds to an OR. So there must be two different cases when we treat the element n as special. But for now, let's read each of these terms literally, and we'll figure out how to stitch them together after. The first term says, pick a partition of the set of n-1 things with k-1 blocks. We want k blocks total, and we haven't placed element n anywhere yet, so we realize that we must be putting element n in a block by itself. So how about the second term? This time we are taking a partition of the set of n-1 things into k blocks. So we've got all the blocks that we need already. We multiply this value by k because we now have k choices for where to place the element n. And notice that this time, the element n is not in a block by itself. So we do have two cases. Either element n is in a singleton block by itself, or it is in a block with at least one other element. So let's summarize our argument. The left-hand side counts the number of ways to partition the set n into k non-empty blocks. In the right-hand side, we treat element n as special. This element is either in a singleton block or in a block with other elements. If n is in a block by itself, then the rest of the elements form a partition of the set of n-1 things into k non-empty blocks. There are Sn-1, k-1 ways to create such a partition. Now, if n is not in a block by itself, then we start by creating a partition of n-1 into k parts. There are Sn-1, k ways to do this. Then we pick one of these k blocks and we add the element n to that block. There are k ways to do this. This accounts for all possible set partitions, and we are now done with our combinatorial proof. We are nearing the end of our video. Our U-try problem for this video concerns the Bell numbers. The nth Bell number is the total number of partitions of the set n into any number of blocks. It follows directly that the nth Bell number is just the sum of the Stirling numbers for the set of n things. As with the Stirling numbers, there isn't a simple formula for the Bell numbers. However, once we've talked about generating functions, we will see an amazing way to express the Bell numbers, so keep an eye out for that in a future video. We will end this video with our U-try problem. The Bell numbers also have a nice recurrence formula. I want you to give a combinatorial proof of it. The left-hand side is the Bell number for n+1. So this is the number of partitions of the set of n+1 things into any number of parts. The right-hand side also counts these set partitions. Once again, we will treat the largest element as special. In this case, the largest element is named n+1. So I want you to treat element n+1 as special and think about what set partitions look like from the perspective of this special element. In particular, I want you to pay attention to the size of the block containing element n+1. Good luck and have fun.